Next speakers are setting up. Let me introduce them. So we have Shuhei and M, and they will talk about the new language server that they are currently developing. And yeah, so whenever you are ready, then the floor is yours.
Thank you. All right. Hi, everyone. Thanks for joining our talk. I'm Shuhei, and this is M. We are software engineers of the compiler team at Julia Hub, and today we will be presenting a new language server for Julia that we have been working on these days. So let's jump right into it. So here is an outline of today's presentation, and first we will give a brief introduction to this language server. And next, we would like to demonstrate the features that are already implemented, as well as some prototype features that we plan to merge soon. After that, we will explain the internals of this language server, and finally, we will discuss the current challenges this project faces, and the future roadmap, and before moving on to the QA session. Okay, so first, let me briefly introduce what this project is all about. So JETLS is a new language server for Julia, and you could say that it's our attempt to create a new development experience by bringing together all the recent tooling technologies in the Julia ecosystem. And as its name suggests, this language server uses JET for its core analysis, but actually it's also built by integrating other tools developed in the Julia ecosystem, like the tooling stack for revise. Specifically, we use JuliaInterpreter and lower code utils for enabling special execution of Julia programs and allows the language server to load user programs in a way it can manage. And it definitely uses JETLS, JET.jl to enable static analysis and error detection for plain Julia programs. And it also uses Julia syntax and JuliaLowering to allow moving freely between source code level and the compiler level. And by combining those technologies, we can support all language features, including macros, while also getting advanced information like type information directly from the Julia compiler and feeding it back to the user. Okay, so I will hand the mic over to M, and she will take it from here.
All right. Okay, I'm a little bit shorter. We already have LanguageServer.jl. What is different? We won't be talking about LanguageServer.jl too much in this talk. Sebastian already did a pretty great job with that, but it is worth motivating our work a little bit, of course. And Sebastian was nice enough to just give us his diagram. So we can just take this and compare and contrast with JETLS. So let's take a look. First of all, we don't really do much stuff in the REPL like this. We do take their LaTeX and emoji completion, so let's like simplify that a little bit. We don't run it in a separate process, so let's just like absorb that box into the language server or something like that. We have better things than CST parser now. We have Julia syntax, and it's in base. So let's replace that. The ghost of tokenized.jl is in there, for those who know. Now the next problem is static lint.jl. As Sebastian said, this is basically trying to replicate some of the functionality of lowering. And I think a very wise man once said that once you try and start guessing what lowering tries to do, problems start occurring. So let's just replace that with a Julia copy of the actual compiler lowering passes. More on that in a bit. And I don't know about all this RPC stuff. We definitely do not use a symbol server, so let's just delete that. Okay, we're almost there. LanguageServer.jl, that looks like a redundant box anyway. Let's just get rid of that. And we are missing a few things. So let's just add JET in there. This is where the box drawing language has started to see some difficulties in dependencies, but JET.jl also brings in some other cool technologies that Shuhei mentioned, and of course, the compiler itself, which I think deserves a big box and also fills up the remaining space. So, ta-da, that is the JET language server. Okay. So I sort of presented that like a joke, but it really is the real answer. There are a lot of things that didn't even exist and weren't even beginning to exist as thoughts in people's heads in 2016. Basically, the fundamental difference is that we have the compiler on our side instead of like making changes kind of against us and we have to catch up. This allows us to do a lot of cool things. We also sort of, we aim to be an enhanced user interface for JET.jl, which right now, if you use JET.jl, you kind of like go to the REPL, you ask for a report, and you kind of, that's a manual process, you interpret the report in all its Unicode box drawing character glory. Yeah, the intuitive user interface for that is just to embed it straight in the IDE, run that automatically when you're done the 5% typing and you're on to the 95% thinking part. Okay, I will pass it off to Shuhei to show off some of the cool features this allows us to have.
Okay, before diving into the demo, let's quickly go over the development status of this project. And I have listed, okay, the basic features that are currently implemented and those we aim to implement in the future. To be more specific, the items with a green checkmark are already implemented, while those with a gear icon are currently under development. And the unchecked boxes represent those we plan to implement in the future. So yeah, but I will demonstrate each of them shortly, so please just consider this list as a reference. And, as a summary of this, I think it would be fair to say that the most basic functionalities as a language server are gradually being put into place. Okay, so let's wrap up the introduction here and actually see what this language server can do. So let me quickly go over the setup first. So for this demo, I will be using a demo package.jl, a sample package. Which is a standard Julia package, about 200 lines of code in total, which has only one dependency of static arrays. And I will be using a VS Code as an example IDE frontend, but you can get similar features in other IDEs like NeoBeam or Emacs, whatever. Also, in the second half of this demo, I will showcase some features that haven't been merged into the JETLS master branch yet. So if you want to reproduce this demonstration, please use rb/demo branch of the JETLS repository. All right, let's start the demo. I will go to VS Code window. Okay, can you see the screen? Oh, yeah, we can see. The font size, can you see? Okay. So this is VS Code with demo package open, and the source file of this file is quite simple. This top-level file only has two interfaces exported, hello and do math, along with this object struct that is used by this function hello internally. And a file named included is included here. So let's go jump to it. And as you can see, some error lines have already been issued. They are called diagnostics in terms of LSP world. And yeah, so first, this hello1 method, which is currently called from hello function here. This function is just implemented correctly, so no error lines are reported here. But for this hello2 method, there is some line which indicates demo package Y is undefined here. This is just because of this typo. And if you look closely, there is also underline here on this argument X saying unused argument X. So yeah, those two lines are just because of this typo, so we can fix it. And if we save it, this error line disappears. So JETLS can report typo stuff, and also it can also report undefined local variables. So looking at this hello3 method, you can see this y variable is returned here, is used here, but it's actually only defined in this else branch. So as a result, JETLS is saying a local variable y may be undefined here, just because it's not defined in this then branch. So if we make this method return here rather than keep going, then the error disappears. So yeah, JETLS is capable to report this kind of stuff too. And yeah, here is a more advanced example. And so because JETLS can fully utilize compiler information, it can also detect method errors. So there is a common mistake that plus operator here doesn't work for string concatenation as like in other languages. But even if we mistakenly use this operator like this, JETLS will tell you, yeah, this plus call would result in a method error saying no matching method found for plus string. So yeah, this kind of analysis is something we cannot get from the existing language server. And to show more complicated example, let's imagine calling a sine function on the result of try pass like this. Yep. Yeah, in this kind of situation, it might be, we might often forget the edge case where try pass returns nothing. But with JETLS, we can see this kind of case quickly because it says this kind of case with diagnostic. So yeah, if we yeah, if we fix like this using something macro, this return is not necessary. Yeah, then error disappears. So this function is kind of valid right now. Okay. To see other features, let's take a look at this doMath method. So this method performs various arithmetic operations on its argument x and returns value depending on the this let argument, which is default to this dicta symbol. And yeah, let's imagine a scenario where we have been asked to debug and fix this method and see how each LS features can help us. So first, let's take a look at tests for this do method function. And the tests are in runtest.jl according to the standard Julia package architecture. And now I would like to introduce a feature that we call inline test execution. So this feature allows you to run specific test cases or test sets in a file directly from your editor. And it uses a package I recently developed called test runner to selectively run specific test cases and display the result in the format of LSP diagnostic. So if you look closely, there is a button saying run a name of test set. So they are the entry points for the inline test execution. And we can click this to run each test set while skipping executing other test sets. So when I click it, we have a progress indicator here. And once the results are back, yeah, we get a result in line. And the errors are displayed like this. And there are a few errors, but let's look at the first exception, which is saying, yeah, this value is simply kind of unexpected value and incorrect. So let's go back to doMath function method. So let's see what's returned for the default value of ret. So if ret is specified as this default value of dict, it's returned here. And from the test case, we can see gamma value here is kind of wrong. So let's use go-to definition feature to see where it's defined. Rather, just use a hover feature. So from this hover feature, it seems like this gamma is just a local variable defined in this function scope. So we can use a go-to definition feature by clicking this variable, go to where it's actually defined. And from this comment, it seems like gamma is supposed to be computed as a polynomial of x according to this, this expression. So I would like to use about poly macro for this, but I don't know how to use it. So I will use a hover feature for about poly, and we can see documentation directly within editor. And according to this documentation, I think I can just place x as the first argument. And now you can see signature help would pop up here, saying that which parameter corresponds to which argument, which parameter of about poly macro calls. And yep, we can write like this. Now let's run the test again. So yeah, it's still running, but now this error is fixed. Okay, so yeah, I think I fixed the first test, but there are still errors, and yeah, this one indicates that we kind of need to handle these kind of edge cases. So let's go jump back to do method, and where it's supposed to be defined. So yeah, this seems to be implemented correctly, and I guess from the test, I think argument error is expected. So let's raise it here, and you can see a completion feature in action here, and also a signature help for those methods. Edge case. Also, completion would work for this kind of case. So it would be easy to change this code to throw like domain error instead, while saying constructors, definitions, and also from signature help here. Maybe, yeah, this kind of, it would be easy to refactor this code. So let's run again. Now the test should pass. Okay, I think I need to handle is none case. Maybe is none. Yep. Okay, so let's run. And also note that there are underlines here too, because this is just because local variable gamma, no, delta may be defined here, may not be defined here. Just because we have this branch, but we already handled this case, we can just simply comment out. Now delete it. Then this function is now kind of clean, so everything works. Oh, so okay, no. Yeah, so this error is from the previous run from this test set execution, but now it runs correctly, so we don't have any diagnostic here. Okay, I showed all the basic features, but finally let me show you a prototype of an interesting feature. So through a feature named inline hints in the LSP terms, JETLS can display the inferred return type for each method. So I have configured my VS Code to show inline hints only when a specific keyboard is pressed. So let's try pressing it. So yeah, now we have a return type, inferred return type displayed here in line. And yep, let's modify this code to exclude this static vector case. Then JETLS will update the code, and the inferred return type is also gets updated. So as you can see, we are making progress on implementing features that utilize type information, and currently we can only show return types, but by fully integrating JuliaLowering in the future, it will be possible to annotate type information for the entire method bodies. Okay, let's conclude the demo, and let's go back to the slide.
All right, Thank you for the demo. Back to this goofy diagram. Let's take a look at some of the technologies that we use inside JETLS, kind of how we use it and how it benefits us. So let's start at the very beginning of the compiler. Claire Foster and Tim Holey did a really great talk about this at last year's JuliaCon. But if you didn't see that, I can kind of very briefly summarize the Julia syntax and JuliaLowering projects. Basically, one of the very main goals is to extend the provenance pipeline from your user input to the compiler, where provenance is just asking, oh, where did this code come from in the user's file? Whether that be a code that is a piece of code that is recognizable to you as like an abstract syntax tree, or some sort of like meat grinder output from lowering, something like that. So we can trace it all the way back. So once upon a time, we had these line number nodes that kind of were embedded directly in the code. It's like, I guess, this contamination in the pipeline, because it kind of is. Basically, there are a few problems with these line number nodes. First of all, we don't get that horizontal provenance, which is not so much a big deal. Like, okay, you got the right line number, it's fine. But the problem is that since we're embedding these in syntax trees and not in like files, not every line gets a line number node, right? We just have to decide places in the syntax tree to put them. And for example, if you have a really long like short-circuiting operator thing that takes up a few lines, that usually just gets one line number node, and that's not ideal. Yeah, so Julia syntax comes along and gives us precise byte-level provenance for every single node in the syntax tree. There's still a problem here, like JuliaLowering doesn't take that kind of provenance. It's still written in FemtoLisp, so we convert that on the way to lowering. This is still a huge improvement in the user experience, of course, because you all have probably gotten an error on 1.10 plus, and it shows you a really nice error message. It's like, here's your problem, here's your code. But you've also probably gotten code that passes through, that makes the parsing pass, but fails at the lowering pass, and it's like, error syntax, $sign outside of quote or something. So the missing piece here is JuliaLowering. We don't actually, the error messages are not even that much of a big deal. The big deal with JuliaLowering is that you can also track backwards through all the lowering passes, which is really important because you know what comes after lowering, right? Yeah, we figure out the types after lowering. And the biggest problem is that we have the types, we don't know where they came from. And in a LSP, or in a language server, that is kind of an issue, right? JETLS is actually able to use JuliaLowering today, just because not every question that you can ask a language server really needs the compiler or JET. It's like, what are the local variables defined at this cursor position or something? So we are able to make use of JuliaLowering right now. Yeah, but we do need JuliaLowering integrated into base for certain features. It's also beneficial to us for a much more mundane reason. It's just written in Julia, so we don't need to go through the static lint.jl type of thing. Where FemtoLisp, you can imagine it as one big red button that says lower, and it spits out a whole bunch of SSA values and slots, and it's really useful for type inference, but not so much to us. We actually just use the first three passes of JuliaLowering to resolve scopes right now. Let's see. Okay, let's move forward in the compiler.
Okay, let's take look at the next phase of analysis performed by LanguageServer. So first, let's assume we have low-word code here. So this is quite a challenge on its own, as you might know from M's explanation. But yeah, we have some low-word code here. And then we analyze this low-word code using low-word code utils.jl and roughly divide it into definition and usage. The purpose of this is that for JETLS analysis, we actually need to load definitions of method and struct into the analysis process. However, if we were to execute all usages like top-level function calls, it would just become a regular program execution, and it's definitely not suitable for LanguageServer purpose. So we need to separate them from the definition code. Then we execute only the definitions using JuliaInterpreter And executing only a part of a program like this is referred to as a program slicing in terms of computer science world. And so in other words, JETLS implements a non-standard executor for Julia programs using low-order code utils and the Julia interpreter. And now JET comes in, and we analyze the usages using JET with abstract interpretation technique. And by doing so, if a function containing an error is called, we can detect such errors without actually executing code. And additionally, JETLS also performs analysis from the definitions themselves, and specifically it starts abstract interpretation from the signature types of method defined by a package, and it detects errors contained within method bodies. So this way, analysis can be performed even if program doesn't have a main entry point or similar, so which is especially useful for package development or analyzing those packages. And after that, analysis cache containing potential errors, type information, and so on is created, and the useful information from that analysis cache is formatted in a way that conforms to LSP and sent to the client via JSON RPC. And this is an overview of the analysis pipeline of JETLS. And for your reference, I added specific algorithms and interfaces used by each component inside of dashed boxes. So if you are interested in more details, please refer to them. Okay, I'd like to hand the mic to M to discuss current limitations.
Yeah, so this all sounds really great. I want cool new features. Should I install JETLS right now? My answer is like, if you're not working on something super huge and you don't already depend on LanguageServer.jl already, and if you like to live on the bleeding edge, I would say give it a shot. It's still very much under development. We haven't bothered making it super easy to install yet. There's a little bit of a process, although there are instructions for VS Code, Emacs, NeoVim, Helix, and Z on the README, so if you'd like to give it a try. If you use LanguageServer.jl right now, you might be missing a few features. So user environment isolation is a big one, where your dependencies and the JETLS dependencies might clash. So we just need to, that's just a bunch of work to do. Some Visual Studio Code specific features are there in LanguageServer.jl, which Sebastian mentioned. And like Revise, we get a lot of power from executing user code, so we would like to do a pass, making sure the effects of that and the safety of that is okay. A few other limitations, as I mentioned, large packages, it takes a little while. Again, if you follow the 5% typing rule, it's fine, but if you're doing a lot of like vibe coding or something, maybe it'll get annoying. If you save the JETLS project and trigger an analysis, it takes about 5 to 10 seconds, but it is still very usable, and both of us use it. We do need to upgrade the caching in that area. Analysis for dependency packages isn't supported yet, so if you jump there, no way back. And of course, it's JET under the hood, so type instabilities can prevent accurate diagnostics. This is just a subset of the many things there are to do. I've personally been working on full integration with JuliaLowering, where this is necessary for the type annotations, as I mentioned, and the precise diagnostics. Yeah, support for larger projects and support for recursive analysis I did mention, and improved diagnostics. We would like to improve the provenance on that, as well as we are working with a Google Summer of Code student who is working on a configuration system, so you get to turn off the diagnostics that are more annoying and stuff. And of course, we want to improve the messages in those as well. All right, I think that's it. Any questions?
I'm curious if you guys have any thoughts on how you want to approach generic functions. So if I have some function in my code base that doesn't have any argument type restrictions, then there's not much analysis you can do in JET without the user supplying something.
It's actually pretty much supported as far as other functions call that a generic function with some signature. So JETLS can start unrises from other functions too. So if other function containing that generic function, it would be unrised. And also, if your test cases containing some function calls that use generic function, that will be also unrised. So I think even if you don't add type annotations to every your generic function, they can be unrised. But just because of type instability possibilities, it's preferred to add type annotations if possible. So yeah.
Since we have you all in the same place, what are your thoughts on integrating these two or replacing JETLS, like taking the core JETLS technology and using it to drive the original language server? Like, what are the parts of the original language server that we need to keep and add to this, and what are the parts that we can drop in and replace?
We did plan for this question. Is this your slide or mine?
Yeah, so there's no immediate plans to replace the language server used by Julia VS Code by JETLS. But in order to do that, integration into Julia VS Code infrastructure would require some work, like implementing its specific LSP features just for the purpose of Julia VS Code extension. So like we need to implement Julia/get module art, but basically it's only the requirement to make JETLS as a backend of Julia VS Code extension. But I think JETLS is still pretty much in alpha at this moment, so I don't have immediate plans to switch, make it possible to use as a backend of Julia VS Code at this moment.
Right, so there are some more questions, but I think we should close the session now and take them afterwards. So thank you again to the speakers, and we continue after lunch with this.